remember, we were trying to prove that certain languages are not regular, that they can't be done by a DFA, and hence they can't be done by a regular expression or by an NFA. And the method to prove that some language, like the intuition of why you have a block of zeros and a block of ones, where the block of zeros is bigger than the block of ones, is you can't do that, is because when you're reading the characters one at a time, and you can't, like a Turing machine, you can't be crossing them off, and you can't be going back and forth, you only can be reading them straight. The intuition is that you have to count the ones, and you have to remember in your states how many zeros there are. And to remember a number between 1 and 1,000,000 takes 1,000,000 different states. But this isn't bounded by 1 in 1,000,000. This is bounded by 1 in infinity. So you need an infinite number of states. And the way the bumping lemma goes is we come up with a set of strings, set of first names that are, each pair of first names are distinguished by the language. And what does it mean to be distinguished? It means alpha and beta, for every pair alpha and beta in the set S that are different, they're distinguished because it could be that they themselves have a different answer in the language, but more than that, there exists the future, there exists a sigma such that alpha sigma may be in the language where beta sigma is not in the language, or vice versa. Everybody remembering that? And if alpha and beta are distinguished in this way, that they have a future which has a different answer, then they can't be in the same state. Those alpha and beta can't go to the same state. And if you have an infinite set of strings such that every pair of strings in that set need to go to different states, then you need an infinite number of states. And if you need an infinite number of states, then you can't have a deterministic finite automata, because the F stands for finite. Right? Everybody get that? So, we're going to do another proof like this. It's going to be pretty much identical to our last one, and then we'll get some other ones. We need a set of first names. Yes?
Okay. So before you start the proofs, I mean, you play the game, right?
Yes.
Good versus bad.
Yes, we're playing the game versus good versus bad. Good point. You know, I'm completely obsessed with the first order logic game. And you know, when a professor is obsessed with something, you should learn it, because it's likely on any midterm which you spent the whole day making up. All right, so here, first order logic game is you have an expression, exists for all exists, and the way you prove it's true is you read it from left to right. And so we're starting with an exists, and when it's an exists, I have to say what S is going to be. I'm claiming that there exists a set of strings, so I'm going to tell you what S is. In this case, S can be the set of strings of zeros, right? And you can kind of see this breaks naturally into a first name and a last name, and so that's why we're doing the first names in S, and then we'll have the last names be the ones. But we'll see that's not necessarily the case. You could have, we could have a different breakup of first name and last name, as we'll see in later examples. But this example is pretty straightforward. So, and then comes the adversary. We're proving that every pair, alpha and beta, have some property. How do you prove that alpha and beta, every pair have a property? Is you say let them be arbitrary. The adversary, the little red guy over there, he's going to say let alpha and beta be arbitrary strings from S. And given that they're from S, we know what they look like. We know that they're strings of zeros. And given that they're different strings of zeros, all we know is that their lengths are different. Right? Then, continuing on, as our friend has said, with the first order logic game, we have exists the sigma. So we, now knowing what alpha and beta are, we have to prove that those alpha and beta are distinguished. And the way we do that is we come up with a future in which alpha sigma and beta sigma have different answers. Well, this is pretty straightforward in this case, because to be the same, to be a yes with alpha, you have to have I1s, right? So we have to gear sigma. We have to gear sigma so that when you tack it onto one of these, you'll get a no, and one of these, you'll get a yes. And then sometimes, which one is it harder? Is it harder to get a yes or harder to get a no? You might focus on whichever one's the hardest to get. But in this case, it's kind of hard to get a yes. You have to have the exact same equal lengths to get a yes. So we're going to focus on getting a yes here, and then hope that we'll get a no in the other one. And so we set sigma to be, oh, I did it the other way around. I was lying to you. I was thinking about equals here. To get a yes, the zeros have to be bigger, right? So what I'm going to do with my alpha and beta, it matters to me which one is bigger, right? So in my mind, I'm going to sort them, and I'm going to sort it so that the alpha is smaller, so that the I is smaller than the J. And if it was the other way around, we could just switch them, switch the names, alpha and beta, right? Because they're arbitrary at the moment, we can flip them, flip their roles. So now, to get a yes, we need the first side bigger. So how are we going to get a no with? We're going to get a no with the alpha in this way, because we're going to make the second part bigger. Right? We're going to make sigma be 1 to the j. And then when we look to see how well we've done, alpha to the sigma is 0 to the I, 1 to the j, and the j is bigger. So you got more ones than zeros. And if you have more ones than zeros, then the answer is no. Right? People following this? Well, it turns out that if they're equal, then the answer is yes. And so we got a yes out of the equals, right? But that still gave you a better understanding of how we're choosing our sigma so that one of them is a yes and one of them is a no, and it doesn't matter which is the yes and which is the no, and you kind of fiddle about so that you get different answers on the two guys. All right? Yes. So we want alpha and beta to be distinguished, and that means that there exists a sigma such that alpha sigma is not in the language, right? Well, beta sigma is in the language. So I could have written alpha sigma is in L, right? Or I could have thought of this as L as a yes-no function. It's all about the same. But the point is that this is a yes answer. And I mean, the one advantage of the L notation is I can say this L and this L, the answers here are different. And I don't care whether this is a yes and this is a no, or this is a no and this is a yes. But basically, one's in the language and one's not. Right? And hence, they can't be in the same state. How are people doing with this proof? How many of you on the 30th could do something like this? We got one person, and he's actually, all right, so what should we do differently?
I just need an example. I just want to have, no, I mean, like, that's the proof, but, like, I want us to, like, have, like, a regular expression or, like, an L, that we actually prove that L.
This is an L.
Oh, well, there we go.
This is an L. And, I mean, we could make things.
I have a quick question.
Yes.
Maybe you can give us like a concrete example of
Alpha and beta?
no, not alpha and beta, but I and beta.
Well, that's alpha and beta. well, then the proof we could say, and hence, no DFA can do it. That's it. This is the proof. This is what you have to be able to do on any midterm and exam, is you have to be able to do this.
You don't have to show a contradiction between say that at some point alpha future will be the same as beta. Because the share state and you don't have enough state for everybody.
Okay, let's try to, since we're having such a complete disaster with everybody understanding, let's just try to go over it all again right from the beginning. All right? So let's say that this thing could be done by an NFA. All right? So out there, here's an NFA that can do it. Then I'm going to do the little gnome thing, and I'm going to convert it into a DFA. Right? And what does it do? It has a start state. It has a bunch of states. It has a bunch of accept states. Right? It has a bunch of edges between them. And this is my machine M that's claiming to read in an arbitrary number of zeros followed by an arbitrary number of ones, and it will land in an accept state if and only if there are more zeros than ones. All right? So I'm going to come over here and I'm going to say, great, I have this DFA, and what I have to do to prove it doesn't work is I have to find one input on which it gives the wrong answer. Right? All right. So I'm going to start by saying, going with my intuition. How many states are in this thing? Right? Maybe there are this many states. I don't know how many zeros I wrote down there. But there are a lot of states. It's a big DFA. Right? So, but I know you got to count up bigger than that. So I'm going to take a single zero and say, where does it go? And I'm going to mark it with 1 because 1 0 goes there. And then I'm going to take 2 zeros. I'm going to see where the 2 zeros go. And I'm going to mark it here because 2 zeros go there. And I'm going to do 3 and 4, 3 and 4 and 5 and 6. And they're going to keep going various places on my little picture. You know what I mean? I'm going to follow 0, 0, 0, 5 zeros, where do I go? 6 zeros, where do I go? And I'm going to keep going until I've counted up to a number bigger than this. Right? And then by pigeonhole principle, what do we know? That there's some node, this one right here maybe, where I've labeled it both I and J. All right? And since somebody, I think she was saying, the cat woman was saying she wanted to be concrete, let I be 3 and J be 4. All right? So if you do alpha 0, 0, 0 and beta 0, 0, 0, 0, they're going to land both in the same state. Right? And I've assumed that J was bigger than alpha, so by a flip of a coin, I happen to get it right. Right? Now, this node here, well, both of these strings in themselves, if you look at them, they're both rejects. Neither of them are in the language, right? And they've both landed on a state that's a reject state. So we don't have any contradiction yet, right? There's no contradiction happening. Everybody's happy so far, all right? But I have an intuition that if at this point the DFA has to, all it's remembered about the past is that it's here, right? So the DFA hasn't distinguished between having 3 zeros and 4 zeros, right? At this point in the DFA's existence, what it knows when it's read 3 zeros and what it knows when it's read 4 zeros is the same. Right? So, so my intuition is what goes wrong is, well, it won't necessarily know what the answer should be in the future. Right? So I have to find some future, some sigma, on which, following from this place, I'm going to get a different answer. And I'm going to set sigma, and this is where I always go wrong, because I never can draw sigmas. They're curly, like something like that. A sigma, so what did I set it to be? I set it to be 1 to the j. So 1 to the j is 4 ones. Right? So I'm going to go from this, and I'm going to go 4 ones. 4 ones, and that's going to lead me to this state. Right? So that means alpha sigma and beta sigma, they're going to follow, they're going to land in the same state. Are they not? They shouldn't, but they are. Why? Because alpha and beta were in the same state, and if we read sigma on a deterministic thing, it's going to land in the same state. From here to here, it's going to follow a fixed path. So alpha sigma and theta sigma are going to go in the same thing. And when we get there, our DFA may be answering yes and may be answering no. We don't know which. Right? It could be answering yes, it could be answering no. But let's figure out what the answer should be. If we do alpha sigma and beta sigma, well, this guy here has fewer zeros than ones. Fewer zeros than ones, it means the answer is no. This should be a reject. Right? But here, we have the same number of zeros and ones, so this should be an accept. All right, so now where's our problem? It could be that this is a reject state, in which case it gets the right answer for alpha sigma. But then it gets the wrong answer for beta sigma. Right? Or it could be that this is an accept state, in which case it gets the right answer for beta sigma, but it gets the wrong answer for alpha sigma. Either way, this DFA is not working. Would everybody agree with this? I feel like saying, praise the Lord. All right? Yes?
How did I and J get into the same state if they're different? Like if it's 3 and 4. How did they end up in the same state?
Good question. Good question. The way it ended up in the same state is somebody who claims that this DFA, there is a DFA, gave me a DFA. And I started by counting the number of states, and it was 10 billion. And then I asked, where does 1 0 go? Where does 2 0 goes? Where does 3 zeros goes? And I did that up to 10 billion and 1. And so I had more, the size of my S was bigger than the size of their DFA. Right? So if you know the pigeonhole principle, if you have 10 billion pigeonholes, and you have 10 billion and 1 pigeons, and all the pigeons have to go in holes, then some hole has 2 pigeons. Or a pigeon died, but we have no, but that would be a problem too, you know, if there was some string 0, 0 that goes off to the dead state, then...
At least 1 pigeon and at least 2 pigeons and 1 nest.
Yeah, exactly. Right? Does that answer your question?
Not entirely. I understand the pigeonhole concept, but I don't know. Like, could you physically show how 3 and 4 end up in the same state? Like, could you have, say, 4 states and then show how, like, if you count 3 and 4, how...
So I can't show you that for sure 3 and 4 end up in the same place. But one of those 10 billion and one ended up in the same place.
Oh, okay, I think it's.
Right? There are two strings, and I would call them I and J that ended up in the same state. We only called them 3 and 4 because we were asked to be more concrete. And the reason I did 3 and not 5 billion is because it writes on the board neater. Right? Yes?
Pastor, so for this example, you just did a proof of contradiction, no? Where you said, okay, let's assume that there is a DFA that solves it, but then it says I can't.
Yes.
Because it doesn't.
Yes.
Because when you say it exists in DFA, it shows that it doesn't exist.
Yeah, I'm proving you give me any DFA, I will find an input in which it gives the wrong answer.
I will give you a DFA with 2 states.
All right, then it would be really easy to find an example where, what?
That's the point.
That's the point, right? So, yes.
What's the meaning without loss of generality and W log on your 5th block right there?
What with this says for without loss of generality, they're sorted, and the reason is because the adversary just handed me 2 strings, and I could sort them if I wanted, or we could say, you know, the adversary is really keen that this one's called alpha and this one's called beta. So I'll say, if it happens to be that I is less than J, then do this, and otherwise do the same thing except switch the role of the I and J. Yes?
So you mentioned earlier, we don't care if it's an accept or reject state where our alpha, sigma, and beta, sigma land. We don't care if it's, as long as they contradict each other, what it actually should be.
Right. The point is, the language is giving a different answer, and the DFA is putting them in the same place. Right? And so they can't have a different answer if they're given the same answer.
And then what's sigma in this case? I get the I and J part, but
Right.
what's the sigma? Now, because we changed the string.
The sigma was the 4 ones.
Something that the language does accept? Or is it?
No, it's something so that alpha sigma is a no, and beta sigma is a yes. Right? Coming from our alpha and beta are in the same place, we follow the same sigma.
Okay, so is the alpha and the beta in the DFA, they give us the wrong answer. Does the language for just those without the sigma, just the language of alpha and just the language of beta, what kind of answer does that give?
So it's pretty easy that if it's just zeros, then the answer is no. Right? So as long as you're reading in zeros, you're probably in a no state. And that's easy enough to happen. You're reading zeros, you're in a no state.
Well, what if your M is 0?
If your M is 0,
0, 1.
yeah, okay, I lied to you a little bit. No, but then you have 0. You have 0, oh, right, okay. You're right. I take it back. So sometimes even with zeros, if M is 0, you need to say yes. So it's going to be yes for a while. It'll be right. You'll say yes on all the zeros, and then at some point you have to switch over to no's when you get more ones. Right? Everybody good? You're ready. How are you guys doing now? Does that help?
Can you go through it again?
All right. Well, you laugh, but the truth, if you want to know the truth of our situation here, is I talk very fast, and we have a finite amount of material to cover, and if anything, we're ahead. So I can go over this stuff as many times as you want.
Like an infinite amount of time? You said as many times as you want.
Until we fall behind in the material, and then I'll start catching up again. All right? So, should I just say the whole thing over again?
Yes, yes.
Sure.
Really?
I think this is going to repeat the same thing and the same thing. So
We
you
can-
prove to someone, to some example,
All right.
Here's an example.
I have an example if you want.
All right.
Or you can do that. Because it's in this, in your slide, it says a to the power of n, b, a to the power of n. Do you want to do something like that?
Yeah.
Okay, you want to write this word? If it's regular or not regular.
Right.
And then L is equal to,
A to the.
yeah, a to the power of n, and then b, and then a to the power of n, and then b, and then a to the power of n plus n.
All right.
And we want such that
Well,
n, comma, m is bigger than or equal to 0.
yeah, n and m are bigger than equal to 0. Yeah, some people got worked up on the last assignment because they thought n could be, the k could be negative, but all right, this is just saying we're doing a math problem, right? We're doing a block of A's followed by a B, followed by a block of A's, followed by a B, followed by a block of A's, and the number of A's in the second block equals the number of A's in the first plus the number of blocks in the second. So we could just as well have this be the character plus and this be the character equals. Right? Everybody got what the problem is? Yes.
Why wouldn't he give you like the slide number? Like it's on your slide.
It's not on my slide. Is this on a slide of mine? No.
Where do you find it?
It's
Was it on his slide? Is it on his
No,
slide?
this is on the questions, like worksheet question.
worksheet question.
Just go on to the worksheet question so we can see it like
Here it is. It's written right there.
we can see it from home. Like when we're looking over it. It's only
It's on the worksheet questions. For those of you who are phoning in from home, it's n plus m equals n plus m. It's go to the worksheet at home. You've upset them. So all right. Now, if those of you who are bored can be thinking about this one, because I didn't want to do this one right now because it has an extra trick that you can be thinking about. All right? All right, so so this one is this one, it's not regular, right? And the intuition is after you read in the ends, you better remember how many ends there are, right? Because otherwise you won't know the answer. And after you read in up to here, you better know how many n and ends there are, or you won't know the answer, right? So our fine Catwoman claims that there is a DFA for this, and she wrote it down on the board here. Yeah, she did. And if it may have 2 states, but it probably has more than 2 states. Right? Probably has lots of states because she's really eager to do this. Right? So here it's this big DFA. And we're going to do the same. I'm going to have the same set of same S, but it's going to be A to the N. Right? My S is going to be A to the N. Right? So it's just this piece here. This is going to be my first name, and this is going to be my last name. All right? And I claim that after you I'm going to claim 2 things. One, that there are an infinite number of first names. Right? And 2, I'm going to claim that after you read in the first name, after you get to the plus, you better know how many A's there are, or else you're going to be in trouble. Right? Everybody in agreement? And that is enough. That's the intuition right there to prove that you can't do it. Right? I'll say it again. I'm breaking each string into first name and last name. Right? how many first names are there? Well, for every n, every positive n, there's a string with NAs. There's the first name with 1A and 2A's and 3A and 4A and 0A's. There's an infinite number of first names, right? In fact, here's the set of all first names, right? A to the n, where n is greater or equal to 0. It's the set of all first names. So there's an infinite number of first names. And then, when the DFA has read the first name, I think everybody will agree that if you don't know what the first name is, you won't be able to necessarily answer the question. Right? All right, so that's the intuition we're going for. What we're going to do is we're going to show that any finite state automata can't remember all the first names. It will get confused between two first names. All right? So we're going to do exactly what we did before. We're going to give it 1A, and its 1A is going to go to this state. And we're going to give it 2A's, and 2A's is going to come over to this state. And 3A's is going to come over to this state. And we're going to keep doing it. We're going to give it every string that's in this list of first names. There's an infinite number of names there, right? So I don't care how many states you have in this DFA. Well, I do care. You have to have a finite number, right? You have to have a number that is a number, not an infinite number, right? So since I have a finite number of pigeonholes and I have an infinite number of pigeons, right? We got some pigeonhole that's swamped, right? But we don't care about it being swamped. We just care there's some pigeonhole that has two pigeons, right? And we're going to give them names. We're going to call one of the first names alpha and one of the first names beta. And those are the first names that go to the same state. Alpha and beta both go to this state, right? And alpha equals a to the I, and beta equals beta to the j, right? And if we want to be concrete, we can have I be 3 and beta and j be 4, right? But we don't need to be concrete here. All we know is that we have different names that are going to the same state. All right, so now everybody on your own, because I know you're going to have to do this, everybody think down, it's a puzzle, write it down. What is my sigma? What is my last name? You can't remember whether I have, remember this is either 0, 0, 0, or it's, oh no, A, 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 or it's A, 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 A. You don't know which, right? So you want to give me a last name such that one of these, so that alpha sigma is a correct answer, and beta sigma is an incorrect answer. So I want to hear from somebody I haven't heard from. Half of you I have never heard from. I could point at somebody.
Oh no, that's a pointing thing.
Yeah, I'm not good at pointing at somebody. Come on, somebody, yes.
Okay, if in a case AM was AA, and AN plus M was 5A.
So what's my sigma? It's going to be 2 A's.
And 5 A's.
And then 5 A's. Excellent. Excellent. And what about the plus? Where does the plus go? Well, we need it to be a proper thing. So let's just put it there. All right? Excellent. She did great. She gets perfect on this assignment. Right? It's not that hard. Right? So we have, note now that alpha is 3 3 A's followed by a plus followed by alpha sigma is 3 A's plus 2 A's equals 5 A's. So this is a correct answer, right? While beta sigma is 4 A's followed by a plus followed by 2 A's, which should add up to 6, but it only gave me 5. So this is the wrong answer, right? Everybody good with that? Yes, I know you do. I can feel it coming at me.
So essentially the biggest problem with this DFA and this language is that it can't count the number of A to the N. So that's infinite. And because of that, it's going to stick multiple things in the same state. And so therefore, no matter what future you give it, it's always going to give you the wrong answer.
Yes. Yes. Let's finish up this example. Everybody got that? What? No, let's finish up this one. Everybody wanted me to go through a whole one again. All right, we gotta meet the people in the back. We have to reach them. Thank you. We have a wave from the back room. He's alive. Excellent. All right, so everybody's getting that alpha and beta went to the same place. So we have this funny sigma. Our friend gave us a funny sigma, but that's okay. We're going to follow from... We're going to follow from this state. We're going to follow sigma, and it's going to take us here. So beta sigma, alpha sigma and beta sigma are going to go to this state. That means that the DFA, what do we know? We know that the DFA on alpha sigma equals the DFA on beta sigma, right? I got my new way of doing sigmas. You just do a squiggle and hope nobody cares. All right? So everybody see the machine is giving them the same answer, right? But we've seen that the language gives them different answers. And how could that be right? That's got to be wrong, right? There's a mistake in there somewhere, right? The machine has to be giving the wrong answer for one of them, right? And hence our DFA that she gave us. Sorry, you gave us a bad DFA.
I did?
Yeah. No. Everybody, how are you guys doing now?
Wait.
Question from the back.
Yeah, I was wondering, can we write it out? Because this system can exist, can we do like how you're doing to give one specific example, or do you want a general thing like they have it on the slide?
Whenever you do it, you have to. It has to be more general. I think if you did a concrete example and I was marking it, I would give you some sympathy marks. But you know, this isn't so hard, right? You know, this is what you need for an answer. Yes.
Can we go over the sigma again? Just the sigma.
The sigma.
Yeah, how did we come up with that A equals like A?
So everybody quiet. Question is, how did I come up with the sigma? And the way it came up, well, she came up with it, but I gave the hint that this was going to be the first name and that was going to be the last name, right? In which case, that's the last name, right? And I get to come up with it, and I came up with, and she came up with it so that one of these questions was right and one was wrong. See, let's fill it out, right? One of them is saying 3 plus 2 equals 5. That's alpha sigma is saying 3 plus 2 equals 5, and that's the correct answer. But 4 plus 2 equals 5 is going to be a bad answer.
No, there is more than one sigma you can use, right? There is not like only one sigma. Like you can change the sigma and still get the same thing done.
You can change it. In this case, there's only really 2 sigmas that would have worked, right? Because there's only given alpha and beta. The only other sigma would have worked is to have this be 6, in which case this would have been a yes and this would have been a no. All right? Now, here, let me, now that we're on the roll here, with this example, let's say that this is the first name and this is the last name. All right? I make these guys work for their money. All right, so what we're saying here, if I keep breaking this chalk into smaller and smaller pieces. You know, one thing, when I work on the blackboard, I sometimes come home covered in dust and trip over chairs. It's a dangerous profession. Yes?
So I'm trying to understand this like general concept. So basically, for this EHSA, there's like a finite number of states you can have, right?
Yeah.
But then like there's like so many infinite possibilities that we don't know that may end up sharing the same thing.
Yeah.
Feature, but they're so distinguished.
Yeah.
We don't know.
Let's try this example here. Suppose I made this the first name. Then I would make S equal A to the M plus B to the M equals, that would be our string, for every N and M greater or equal to 0. Right? This is the whole first name. Right? And, oh, sorry, where did you get the A from? The B. He was right. Keep me on my toes. All right, so, yes.
Who chooses the first and last name?
You get to choose S. So you're choosing the first name. You get to choose sigma. So you're choosing the last name. So it's 100% you. You is the prover. All right? Now, the intuition here is that all of these guys are distinguished, right? If you gave me 2 of them, 3 plus 2 and 4 plus 2 equals, I could say my sigma is 5, and so that this is a right answer and this is a wrong answer, right? So that would feel like we're doing fine, right? Except there's a bug here. What's the bug here? Nope.
Different ends, right?
Different ends?
And different person, more than one.
N and M are different.
There's more. One is 2 more than the other.
Your inputs are the same. Your futures, no. Your inputs are different. The futures are the same.
Could
but
you
your
give
answers are
me-
different.
Yes.
The inputs are different.
If you don't have an A, N plus N after the equal sign.
No, I would have the beta be some number of, here I can make beta be 5 A's, right? If I was trying to distinguish 3 plus 2 and 4 plus 2, I could easily distinguish them by giving an answer of 5.
Is the bug that you can have 3 plus 2 or you can have 2 plus 3?
Yes! Yes! All that's being promised here is that the first names are different. So the adversary could really give me 3 plus 2 and 2 plus 3. Right? The adversary gave me different first names, and it's perfectly reasonable for the DFA not to distinguish them. Right?
But that wouldn't matter because we only have to find one such that it is contradictory, right?
We have to come up with a set S such that every pair are distinguished. And we came up with a set S that there are lots and lots of distinguished guys in there, but they're not all, every pair isn't distinguished.
are equal, so that string is the same as the next string. So 3a plus 2a is going to be equal to 2a's plus 3a. So that's not a bug. I don't think that's a bug.
It's a bug in proving that the DFA doesn't work.
Well, the first DFA is actually going to end up with 5 of both scenarios.
So the DFA is working, so it's not a bug in the DFA, so it's a bug in our proof that the DFA doesn't work.
Oh, the first DFA doesn't work.
Yeah, right. But here's a way of fixing it. Let's limit our number of first names. Let's have this first one be 1. Right? My set of first names used to be any number of A's and any NA's and MBA's. Right? But I've limited M to being 1. Right? These are the first names that I care about. Right? So it's still an infinite set, but now I'm claiming that they're distinguishing. Right? Because we know that the second digit is a 1, and we know that they're different. Right? The first names and the second name have to be different, and their second number is a 1. So we're back to everything being fine. Are people following that?
No.
About this?
Yes.
All right, what's your question about this?
Basic math. But other than that, my question is that, so the issue with this DFA is that it's not distinguishing between 2 different inputs when it should be doing so, because the language is doing so.
Are you asking about this?
Yes.
All right.
Great. So, as I was saying, the DFA is not distinguishing between 2 different inputs when it should be doing so.
Yes.
That's the problem.
That's the problem.
Well, the language is able to distinguish between them because it's the language, right? The DFA
Yes, the language is distinguishing between them. Yes.
But the language and the DFA are giving 2 different answers, so therefore
Yes.
it doesn't work.
Yes.
Okay, thanks.
It wasn't about this. This is...
Can you go over that thing?
All right, so I'm claiming that this would be an excellent answer. All right? Did everybody understand why the M here did not work? Should we go over that again?
Yes.
All right. So I'm saying this set of first names aren't all distinguished. Somebody, I forget who, somebody quite brilliant came up with 2 plus 3 versus 3 plus 2 equals. So this and this are 2 first names. They're different. 2 first names in my set of first names. Agreed? Does the language distinguish between them? No. So it's not the case that for my set of strings, for every pair of strings, they're distinguished. It's not true. Right? I gave you a far too big set. Instead of giving you a set of size infinity, let's just say I gave you a set of size infinity squared, but we'll prove later that what I'm saying is crazy. A bigger, I gave you, a bigger set of infinite strings. Right? So I want to, right, suppose, if this set is like this, and I have a red one here, and a blue one here, and I have a red one here, right? These 2 red ones aren't distinguished. They're the same. So what I'm going to do is I'm going to make my set smaller so they're all different colors. Right? Everybody see what I'm doing?
Using that, how can you relate to that?
Well, let's do it more concretely here. Here's 2 plus 3 equals, and here's 3 plus 2 equals, and here's 2 plus 4 equals. These 2 are distinguished. These 2 are not distinguished.
Those 2 are not distinguished over there.
These 2 are not distinguished. So I'm going to limit my set down to I to n plus 1. I'm only going to consider those that are n plus 1 equals. Right? I'm going to have a smaller set of first names. It's going to be a to the n, a to the 1, 1a equals. Now I claim any pair of them are distinguished, right? They have to begin with 1. I mean, they have to have a 1 in the second place, and they have to be different. If they're different, they have a different number of a's in the first place, and so their answer must be different, so they're distinguished. Yes?
Aren't we changing the DFA itself by changing the M to 1?
No. No, the DFA that she gives us is the same. What I'm changing is I'm going to run her DFAs on all of my things in S, and so I'm going to run it on a smaller set. I'm going to test her on a smaller set. Right? Her as a student is the same, but I changed my exam. Right? I changed my exam so that I only have questions on my exam that have different answers. Yes?
Sorry, in this case, we're in a condition that n is more than or equal to 0. So if we say a is to the power 1 plus a to the power 1, they won't be distinguished if you alternate them, would they?
Well, that's one thing. You're making alpha be 1 plus 1. All right, and then what are you going to make beta? It's got to be different, right? Yes?
The N is the first name, the M is the last name, is it? No, I'm confused now.
No, now I'm doing it where this is the first name and that's the last name.
What's alpha, beta, and sigma in that?
In this example, this is alpha. This is beta. And our sigma, here the answer is 2, here's the answer is 3. Right? So we'll make sigma, however you do the sigma squiggle, will be 2, so that alpha sigma is a yes. Right? And beta sigma is a no. Right? Is that making sense?
How can we write it in the general, like, full mark notations, not the sympathy mark notation?
In the full mark notation, I would say let alpha equal a to the I plus a equals, and beta equals a to the j plus a equals, where I doesn't equal j. And then let sigma equal a to the I plus 1. Right? Then alpha sigma is L of a to the I plus a equals a to the I plus 1, which is a yes. Right? But L beta sigma is L to the aj plus a equals a to the I plus 1, which is a no. Right? And hence we know that S is fully distinguished and is an infinite set, and hence we know that there's no DFA for it. How is everybody doing here?
You said that changing the M to 1 does not modify the actual DFA. So what if you leave the M as 1, but then you also change the N, right? Then that would start modifying it?
Sorry, now, what are you doing now?
If you leave the M as 1, which you have right there.
Yeah.
Right? Now if you change the N as well to anything, sure, does that modify it from the original DFA?
Now how many things are in your list of first names?
One, yeah.
It's not very infinite, dude.
So is the N, because there was an N, there's an infinite amount.
Yeah.
So it didn't matter that we had NN
It's still infinite. Right? Everybody good?
Yes.
Anybody have any questions? How many people now feel that you could pass a question like this?
Pass it. Yes. Full marks.
Well, yeah, I was that's what I want. I want everybody to pass.
So question for you then. So, if we write the wrong proof, would we still get partial marks?
If you say, Bob's your uncle, you'll get 0 marks. Actually, there's a TA who's marking the second test who took some course from me somewhere. And she reminded me that what I often do on tests, if you leave a question completely blank, let's say one of you leaves the question completely blank, and one of you writes insulting things down, right? Proves to me that they do not understand what's going on, right? Which deserves better mark? The blank paper, right? The blank paper deserves better mark. So I have been known, when I'm really pissed, to give negative marks on questions. All right? But my experience is that people don't like that. I don't know why, but people have just a sort of gut reaction against giving them negative marks. And the other thing I find true is that, 50%, why is that the pass? Right? You could have the pass be, it's just an arbitrary number anyway. So what I've been known to do, and we can do that if you like, if you leave a question completely blank, you get 20%. Right? You get 20%. Now, if you leave the whole exam blank, this is for real. This is for real. You leave the whole exam blank, do you know what's going to happen? You're going to fail. Right? She's on the ball here. 20% is still not a pass. Right? But the advantage of it, if you're running out of time, then you're not hit so bad by a 0. Zeros hurt. Right? And if you think, I just don't know how to do it, then it says, don't insult me by putting garbage down. I don't want to mark it. You don't want to write it. Right? Hear what I'm saying? So that's where we're going here. Now, I would say for the assignment, I agreed with her that she can do that. But I would say for the assignment, you shouldn't bother because you have plenty of time to work on it and get it right. Right? But actually the truth is I do that without having told people in the past. Right? If Bob here, he handed in all the assignments and he did okay on the midterm, but for some reason I just don't have a mark for test 3. I'll sometimes write him and say, dude, did you write test 3? What happened to it? He'll say, no, I was with my girlfriend. Right? And then I love that honesty. And then I just give him 20% for it. Right? Well, because he left it blank. And he had a good time with his girlfriend. I mean, that needs to be rewarded. All right.
You're a hero.
It still won't, as she says, it still won't pass you.
The biggest issue that comes with this thing, I don't even know if I asked that. The biggest issue that comes with this thing is because your ends or your A to the ends are infinitely perfect. So we can't even count, because we have a finite DFA, we can't even count A to the end. So what the hell is the point about thinking about the future, because I'm going to get it wrong anyway. The whole crux. In fact, if you could take one lesson home from this entire course of what we've done so far, I would say it's that the machine is finite and the language is infinite. And so it's not so easy
to write a finite machine that would give the answer on an infinite number of answers. And that's the crux. All right, so how much time do we got here? We still have 10 minutes or so.
What's the trick with the next example?
So let's look at the next example. That's what we're going to do here. Here, the next example. All right, so
Because to me, it's all.
all right. So now we're going to try to do a proof here, and the proof is going to fall on its head, and we're going to see why does the proof fall on its head. And we'll go back and we'll see what people have to say. All right, so we try having a set of infinite first names, and we were smart enough not to have the first names be too small. We knew to be significant they had to have at least 100 ends, 100 zeros. So we had that be our set of first names, and that was good. And then our adversary gave us two of them that we need to distinguish. And how do we distinguish, right? How many zeros there are, right? Isn't linked to what n needs to be, right? As long as n is greater than 0, then they're not distinguished. I don't need to know. When I read the zeros, I don't need to know how many zeros there were. Right? Because all I need with the ones is that there are at most 100 of them. Right? So there's not a linking here between the first names and the last names. Right? Everybody see how this proof is failing? And why is the proof failing? Somebody has said it already. Why is the proof failing? Because there's perfectly good DFAs that do it. All right? Right? So if we break it into two languages, the language that counts up to 100 and makes sure that there's at least 100 zeros, and then the DFA that counts up to 100 and makes sure that there are at most 100 ones, those are clearly regular. Right? And then you concatenate them together, and it's clearly regular. Yes?
It's not regular.
It is regular.
Okay. How they're
Okay. My bad.
I can't see it. It's too
If I gave you 105 zeros or 106 zeros, would you care which it was when you were reading the ones? You don't care. You don't care. After you read the first names, all you have to know is whether or not the number of ones, the number of zeros was bigger than 100 or not. That's all you have to know. You need to know one bit. Right? So they're regular. I'm going to say it's regular. I'm going to say I don't have to remember how many zeros there are. Right?
So what if it was 0 to the n and then 1 to the n plus 1?
0 to the n, 1 to the...
N plus 1.
Oh, yeah, well, that's clearly... That would be just the same as everything we've done so far. It's clearly not regular. Right? Right? Are people getting this? So, you can count on there being one of these on the midterm. You know, is it for sure? No, except I did work on the midterm all today. Right? You can count on it. And you're going to have to know, is this a regular language? Is it not? You're going to have to prove whether it's a regular language or not. Right? So you learn this stuff. Any other questions for our remaining 9 minutes?
I don't see how I don't understand.
All right, which did you not understand the fact that it is regular? All right, so here's another question. We can do review on other topics. I'm gonna make the 100 a little smaller, but let's make it, what do we got, A's or B's? Zeros. 0 to the n, 1 to the m, where n is greater or equal to 2, and m is less than or equal to 2. Right? So, you should be able to do a DFA for this. Right? You just say, you know, I got one of them. I got two of them. Oh, they're zeros. Now I have greater or equal to two of them. This, if I'm in this state, I'm doing an NFA for it. Now I'm really happy that I got a bunch of, at least two. And then I got a 1, I got a 2, I got another 1, and now I have lots of 1s, right? Where do we want to accept? We want to accept here and here.
What about
Should be a union or not?
Should be another state.
Yeah, we need one more state for fail.
Well, this is all fail here.
So less than equal to 2.
Less than equal to the one that
Well, this is an NFA. If you get,
Put a 1 instead of 1.
or one, yeah, you need to at least have two
I got 1, 1.
two ones except
Oh, equals. Oh, you're right. It's equals. I got 2 of them. I accept. Now I get anything else, and I'm dead. In fact, we can just do it right there if it's an NFA. That's a perfectly good NFA. Right? Everybody good with this NFA? So if an NFA can do it, you can stick little gnomes on it and convert it over to a DFA. So a DFA should do it, and hence it's not unreasonable that we can't prove that a DFA can't do it.
In that example,
Yeah?
they're like, how are they like, there's more zeros than ones, right?
Yeah?
How are they like, not integer?
There are more zeros than ones only because they're limited by 2. Right? The difference is, if your job is to read in the zeros and her job is to read in the ones, what do you have to think about it this way? It's a communication game. All right? Here's a new way of thinking about it, everybody. I'll get to you in 1 second. A communication between the first name person and the last name person. Right? The first name person reads in the first name, and then the last name person will read in the last name. How much communication needs to be between them? Right? In this example, the first name guy has to say, we're okay, dude. We got at least 100 zeros. Right? And that's good enough. In this example over here, the first name person better tell you exactly how many zeros there are, or the second name person can't do their job. Right? Communication game. Yes?
I have one question for, like, let's say the previous question when we had 3 A's and we split it into 2 groups. If you have any questions like that on the test, is it okay if we prove that for the first part we cannot create an NFA, a DFA, because the whole...
Sorry, I'm missing what your first and last parts are.
The previous question we had.
This one?
So if we suppose prove that AN plus AM is not a DFA.
Well, this is. That is, we could recognize that. But how much communication has to go between the first name person and the second name person? Right? You have to communicate what the sum is.
Okay. No, I was talking about like we had that scenario that we cannot distinguish between 2 plus 3 and
3 plus 2, right.
Yeah, if you prove that we cannot distinguish between those two, thus this is not a DFA?
No, it means your proof didn't work.
Oh.
Right? You just had the wrong S.
Okay.
Yes?
Can we like generalize it as like in here, if N and M are dependent on each other, then there's no DFA. But if they're independent, there is a DFA.
That's a good rule of thumb. But not totally, right? Because if I said the parity of the zeros equals the parity of the ones,
But they're still dependent.
they're dependent.
Yeah.
But the first named person reads in the zeros and he learns the parity of the zeros. All he has to tell the second named person is what the parity of the zeros is. Right? There's not an infinite, there has to be an infinite linking. A finite linking isn't good enough.
Say if you have to transmit the answer of a yes or no question, you're good, and if you have to transmit some precise result, you're not.
Yeah. Yeah. All right, we're good? 2 more minutes. This has been a little bit more of a tutorial. Yes.
A sample question that just popped in my mind. Can we do AN? Remember, it's N plus N, where N is always greater than 1.
Is that really what you want?
Yeah. Like if we want to prove this one, what are the steps to do this? M is always 1 greater than N.
M is greater.
N plus 1? It's N plus 1, yeah.
Well, this is the same as A to the 2 times N plus M, which is really the same as A to the even. So I would say this is regular. All you're really asking is there an even number of A's?
Is this going to be a DFA or no?
A DFA could do this because there's no marking in between. Right?
But you can't solve for how many N's plus M there are, right? There is no machine that can count N plus M.
No, but all you gave me is a string of 2 times N plus M A's. Right? So all I have to know is the string of A's even. Right? If you put some sort of marking in between, then it's the same as we did before. Very good question.
So you always have to distinguish between
Not always. We'll be looking at other examples.
But for you, you have to know what N is the second part, right? While counting the M. You have to know.
No, because the DFA doesn't have to know where it's switched. Right? DFA doesn't have to know that. All right, I think we're done. We ran out of time. We ran out of enthusiasm.